Welcome to lecture number 28. Today we are going to cover a topic that majority of the textbooks cover during the postulates of quantum mechanics. But here we are now covering it at a bit later stage. So you will later find it out soon that why I feel it is more appropriate to talk about commuting of operators in this lecture. Okay. So before we begin, let's first give an example that we understand Heisenberg's uncertainty principle. Alright, and the way we understood it, that for example we have seen it for a particle confined in a 1D box or for a simple harmonic oscillator, then we have seen that the uncertainty of position multiplied by the uncertainty of momentum came out to be something like this. Alright, so that means you cannot simultaneously measure both the position and the momentum. So that is the central idea of Heisenberg's uncertainty principle. Now, position is an observable and the momentum is an observable. And we know that corresponding to every physically observed quantity, there exists a quantum mechanical operator. So for which x is the operator for position and px cap is the operator for momentum. Alright. Now the question is that is there any special relationship shared between these two types of operators so that they are linked by the Heisenberg's uncertainty principle. Alright. In other words, can I say that suppose A is an operator and B is another operator, and correspondingly their physically observed quantities are A and B. So the question is, what relationship, or is there any special kind of relationship between operator A and operator B so that this condition is followed. That means these two observables satisfy the Heisenberg's uncertainty principle. Alright. So now the answer is that yes, there is a certain kind of relationship, and that relationship is called commuting relationship, or in other words, this is called the commuting operators. Alright. So what do we mean by the commuting relationship? So to understand it in a better way, we should try to follow the formal definition of it. Alright. So the formal definition says that if there are two operators A and B, okay, and if I represent them by this symbol, so look at the symbol. I have written the A operator first and then the B operator. It is just not I have written it arbitrarily, but for a purpose I have written it A first, comma, and then B second, and I have put them within the square bracket. This is a symbol, and symbol means it has a meaning. So it stands for an operation. An operation is A, okay, A operator is working on multiplied by B operator, okay, minus B operator again being multiplied on the A operator. Alright. So this is the meaning for it. Now there are two outcomes. That is, this AB minus BA could be 0 or it could be non-zero. Alright, because something being subtracted from something, so there are only two possibilities, 0 or non-zero. So whenever the difference is 0, we say the two operators commute. Alright, and that means you can, then also we can write it here, or okay, so we should talk about this first and then we'll come to the non-zero case. Then that means that we can simultaneously measure both the observables, or means both the physical quantities A and B. Alright, but if this is non-zero, okay, so we say that the two operators don't commute. Alright, and then we say that the observables A and B follow Heisenberg's uncertainty principle. Alright, or simply the corresponding equation we can write that this is equal to or greater than equal to half H cross. Alright, so you can take this expression as a kind of theorem of quantum mechanics, or one of the kind of postulates of quantum mechanics. So the bottom line is, if this is 0, they commute. If they don't zero, if it is non-zero, they don't commute. And the outcomes or the significances are clearly written it here. So from our next derivations and for the next subsections that we are going to study, we will follow this the outcome of the commuting relationships. All right. So like this, there are few more basic relationship that starts with this one, and we can call it a kind of a sub postulates or something like that. And so let's clean the board and let's try to read those expressions like a bunch of basic formulas. Okay, so let's do that. Okay, so here I have written the fundamental formula, the fundamental expression for commuting operators, and then these are the corollaries that can be derived from this above relationship. But anyway, for the time being, we are going to remember for the first 4 or 5 expression as standard formulas. So I can mark it as equation 1 and this one is equation 2. So it says that when you write it in a reverse manner, that is when you do the operation with the B operator first and then the operator A, remember, okay, so there should be a comma, I missed. So remember, there will be a negative sign appearing. Alright, so operator A first, then operator B is equal to minus of operator B first and then the operator A. And then we have operator A commutes with any nth power of the operator A, where it is equal to 1, 2, 3 integers. And then if we multiply by any arbitrary constant in any of the operator, it is same as multiplying with the other operator by the same constant, and eventually this has no effect and the arbitrary constant can come out of the commuting relationship. And then here we have upper A comma operating on the summation of B plus C. So it can be broken into A comma B plus A comma C. All right, and similarly, A plus B C, it can go to, I missed the commas, sorry, A comma C plus B comma C. So like that, we can write A comma the product of B and C, and we can write product of AB comma C. All right. So now we can mark it as equation 3, equation 4, equation 5, equation 6, equation 7, and equation 8. All right. So all those 8 equations we may want to remember why we are giving these numbers and importance, because for the next few workouts, what we are going to do, we may need to take the help of one of those equations or one of those relationships. All right, so let's figure it out. So let's start with one simple example. All right, so let's do it. So let's assume that operator A is ddx and B is x. So can we find A comma B? All right, so whether A, B commute or they don't commute. All right, so what we find, we have to find that is the value of this, whether 0 or non-zero. All right, so how to find it out? So I will work it out one example for you. For this kind of problem, we will start with assume the function is equal to f, which is any arbitrary function. Okay, so we have to find out AB is operating on, means this relationship is being operating on f. All right, so this is equal to A B F minus B comma A F. All right, so when we do this, it should come to A is operating on BF minus B is operating on AF. So basically the significance of this statement is this. So now let's find it out. So what is our A? Our A is ddx. All right, so ddx of our first thing is the operator B is x, so it should be the product of x and f. So ddx is getting operated on xf minus x getting multiplied on df dx. All right, now look at here, this is a product between two functions. So once we start to derive, we do is like f constant, the ddx is getting operated on x, which is basically 1. So f plus, we have x comes out and we have df dx. All right, and we already have minus df dx here, so those two cancel out and we have f. So what we get here, so what we get is basically this. So we started from this and ended up with this. So we have ABF is equal to f. So in other words, we want to eliminate the function f, then we find out that the relationship between these two operators, okay, that means ddx comma x is basically 1. All right, so it also means that if we take these things in terms of partial derivatives, so it also means that del x comma x is equal to 1, or x comma del x is equal to minus 1. All right, so we have easily proved that ddx and x, do they commute? No, they don't commute, because the relationship comes to a commuting relationship comes to a non-zero value, which is 1. Alright, so now it's your turn to do the next exercise. Alright, so let's write it out for you. Okay, so I have given you to solve this relationship xpx. So we all know that those two operators don't commute. So the question is, if they don't commute, what should be the value comes out from their commuting relationship? Okay, so can you do that? I'm sure you will be able to do that in this way. So let's expand this thing as minus I h cross ddx. Alright, or we can in fact directly write as del del x, no issue. Okay, so as we have seen from the equation 3 or something in previous relationship, because if there is a constant, the constant can come out of this commuting relationships. So it gives you something like this. All right. Now this is equal to, we can write it in reverse. Okay. So that means del del x comma x cap, but it should be followed with a negative sign. So that negative sign will come out and make this as positive quantity, positive IH cross. All right. Now, just few minutes ago, we have proved that this relationship, that is the ddx comma x or del del x comma x, is equal to 1, unity. So this is equal to IH cross. All right. So what we get is x comma px is equal to IH cross. So that's how we find the value. All right. So this is very easy. So I'm sure that you have done it. So you will do few more things for me. All right. And I'm writing it out. So you are going to find out x comma px square. All right. Now we can easily write this as the product of two operators, means px multiplied by px. Okay, and from one of the previous formulas, you see now the formula number 1 to 8 that I have written previously would now come and help us. So following one of those formulas, which one, you please find it out. We can write it something like this. All right, plus all right, and then we can further expand it. So x comma px, we have already found out that this is IH cross. So we can write IH cross, and px is minus IH cross del del x, all right, plus once again minus IH cross del del x for px, and xpx is once again IH cross. So that gives me I multiplied by minus I, that is minus I squared, this is minus 1, h cross squared, so minus h cross squared del del x, alright, and once again here minus h cross squared del del x, okay, and it gives me minus 2h cross squared del del x, alright. So here did I make a mistake? So I times I means I square means minus 1, so minus sign already there, so yes, I made a mistake. So this should be plus and this should be plus, so this should be plus. So this value is equal to 2h cross square del del x. Okay, so once again we got that the position operator don't commute with the square of the momentum operator. or in other words, the position don't commute with the kinetic energy operator, because px square cap by 2m is the kinetic energy operator. And then the relationship between x cap comma px square is basically 2h cross square del x. Alright. So now you have got a clear idea how to deal with such kind of expression. So following those, now finally you have to solve one or two basic relationships. Okay, so I'm going to write it down, some of the expressions of the commutation relationship, and it's your job to find out the final value. Alright, so I have worked out 3 examples for you. So now it's your turn to work these 3 examples. Okay, so before we finish today, I would like to make a strange derivation for you. So the relationship that I'm going to derive, it comes from the standard Heisenberg's uncertainty principle. So we know that the product of uncertainty of position multiplied by the product of uncertainty of the momentum, or in other words, the standard deviation of or this root over of the standard deviation of position and the root over of standard deviation of momentum is greater than is equal to half h cross according to the Heisenberg. So, or we can write that this is equal to greater than is equal to half h cross, it is multiplied by 1 and multiplied by 1. Alright, now this is not a very ideal way to express an equation like this, but we are going to get some end product out of that, and we will only concentrate on the outcome, not the process by which we are getting it. So, because the derivation looks pretty silly. Anyway, let's continue. That we cannot deny this step from that step, so this is technically correct. There's no problem. So once again, this one I can write it as a modulus of I. Also you cannot deny, because the mod value of I is 1. Alright? And then this one we can also write that it is this integral. Alright? So when we assume that psi is normalized, okay? So when psi is normalized, so psi star psi d tau over the total integration limit is equal to 1. So we have back calculated or back expressed in backward manner the expression of 1 by something like this, because we are going to prove something. Or other words, or we can write that delta x multiplied by delta px greater than is equal to, I can keep half outside, and what I can do is I can now include this IH cross, because this is a constant, so I can include this IH cross term inside, okay, something like this, IH cross psi delta. Alright, so we can write like that from here to here, okay, so we have no problem with that. So now the question is, look at this expression. All right. Now, okay, here once again, I have made a mistake. I have to correct that. So this was the mod value, modulus. So the moment I include the mod of I inside, I can directly write I. Okay, I don't need to write the modulus of y once again. Okay, so this is IH cross inside. All right. So this is also correct. So or delta x multiplied by delta px greater than or equal to half. So can I further replace IH cross with something? Yes, we have just seen that this relationship, that is x cap comma px cap is equal to IH cross, that we have seen a little while ago. Alright, so I can replace this thing with that. So therefore now we have a distinct and a special relationship. So the relationship, once again, I'm writing it here, that is the product of delta x and delta px is greater than or equal to half within mod value. Alright, so I forgot the integration. Integral psi star x cap comma px cap psi delta or d tau. So that tells me something, a general relationship. That is, we can replace x as an operator a and corresponding observable is a. So delta a multiplied by delta b greater than or equal to half psi star a comma b psi d tau. Alright, so now we are having a fresh relationship, that is the two quantities. Alright, if the standard deviation of 1, the product of the root over of standard deviation of 1 and with the root over of the standard deviation of other are linked by Heisenberg's uncertainty principle, then they follow this kind of relationship, that is delta A delta B is greater than or equal to half of this integral. Okay, so that means it automatically tells me that this should be equal to greater than half of h cross only when this value not is equal to 0. Got it? If this value is equal to 0, that means if A and B commute, that means if A cap comma B cap is equal to 0, then we can simultaneously measure A and B. Alright? Because then this integral would become 0. So the Heisenberg's uncertainty principle would not be followed. So as long as the two operators do not commute, this relationship is maintained. Alright? And we have seen that if A and B is replaced by x and px, this value comes out to be IH cross, and that is the basis of the original relationship, that is product of delta x and delta px greater than or equal to half h cross. In fact, it is not only for x and px, there are other two commonly observed quantities, that is delta E and delta T. Okay, so these value comes, these observables become relevant in terms of spectroscopy. Suppose if I want to measure the energy of an excited state and the time it spends, that is the delta T in that excitation value, and the accuracy of measuring its energy can be defined as delta E, and the uncertainty in measuring the time value it spends in the excited level, delta T, is related with the Heisenberg's uncertainty principle. same way, that is radian is equal to half h cross. So that means if the uncertainty of measuring energy is 0, then the thing would remain in the excited state indefinite times. Alright, and if we for sure if we can measure these the time, the uncertainty measuring time in the excited state, then we cannot measure its energy. Alright, so I guess this was one of your questions at the very beginning, that except x and px, what other observables follow Heisenberg's uncertainty principle. So now it is true that it follows by that, and also we have learned an interesting expression the operators follow in order to satisfy Heisenberg's uncertainty principle. So in this lecture we have learned some very basic things about commuting operators and the consequences when they commute and when they don't commute. And I think we need these little basic knowledge and commuting relationship when we move on to our next topic under the same big chapter. And our next topic is the angular momentum. So I will see you in the next lecture. Okay? Till then, goodbye.